Well, once again, something practical, although with a bit of maybe deeper science, at least from material point of view. So here we deal with impact toughness of certain more or less classical carbon steel used for welded structures. And here we focus on the welded joints because critical area in respect to impact toughness or any toughness, as you know, of course, is in welded joints, either heat affected zone or weld metal. We do have TC18, by the way, to deal with that. So this is what is also written here. We have used the instrumented Sharpie toughness pendulum, which can separate crack initiation and crack propagation energy, which is very important issue. As it turned out, in this case, not so important. For what we aimed to do, it was almost irrelevant because we actually tested these welded joints starting from the room temperature down to 0, -20, -40, and -60. And the idea is to evaluate ductile to brittle transformation temperature. Actually, our main task was to find out how these welded joints behave at -60, because there was an idea to use this steel as a pressure vessel, as a tank for CO2, liquefied CO2, which is operating at approximately -60. As I told you, this steel is low alloyed, very low alloyed carbon steel used in pressure vessels, just as I mentioned, for storage. And it has, well, not exceptional, but good mechanical properties. Whenever I take data from literature, all mechanical properties are exceptional. I don't know if you notice that as well. So be more realistic. Good one. Actually, the best feature of this steel is that it is cheap, and still it can serve as a good material for many applications. In this case, plates were of thickness of 15 millimeters, and welding was done by manual arc process with some advanced electrodes, alloyed with nickel. I'm not sure that I have tables 2 and 3 here. Let's see. No, I don't. It's in the paper. Sorry for that, but it's quite classical. Nothing interesting too much. You can see, well, barely you can see in this figure here how weld metal looks like. There were a couple of passes and X type of groove. Microstructure, typical for this type of steel, and then for heat affected zone and for fusion zone and for weld metal, pretty different type of microstructure, although you will see that behavior from point of view of impact toughness is maybe even unexpectedly similar. When I first saw these microstructures, I thought that it would be the difference would be much more expressed. So Sharpie instrumented pendulum, it's how to say, almost forgotten but very practical tool to at least estimate, if not evaluate, material behavior, material crack resistance to cracking. Material crack resistance, sorry. So what we get from this instrumented pendulum is force versus time diagram, and then using it we can separate energy to initiate crack, which is practically the area up to this point, and then energy for crack growth, which is remaining area. In this case, you can see that energy for crack initiation is much larger than energy for crack propagation. Knowing data like this, you can conclude about crack behavior of material, because if crack initiation energy is much higher than crack propagation, that is one way of crack resistance behavior, and completely different is the other option. If we have material with low crack initiation energy, then we have to be much more careful with its initial state. To be extreme, I can say such material must not contain cracks. So, in any case, we did testing, as I just explained, and obtained typical curves, obtained curves for force versus time for heat-affected zone, for weld metals, for base metal, and then some of them, as typically obtained, are shown here at -60. Focus was here on -60, and on getting temperature dependence of total energy versus temperature. So here we have, as our final result, base metal, heat-affected zone, and weld metal. You can see at once that it's quite similar. In my experience, which is a big one, differences are usually bigger than this. So this steel behaves nicely in a sense of its welded joints. Using diagrams like this, if we put 27 joules as a limit, we can get ductile to brittle temperature transition. It would be somewhere here for base metal, somewhere here for heat-affected zone, and somewhere here for the weld metal. More concretely, base metal had it at -70, heat-affected zone at -65, and weld metal approximately at -62. Since our idea was that we use this steel at -60, we can say that it has passed the examination. We can use it, although it is quite close to being not usable. But to emphasize once again, these differences are really not big. So having weld metal, which is with high enough impact toughness at -60, that's good news. That's really recommendable for this steel. Now, just to explain why I didn't mention anymore crack initiation versus crack propagation energy. Here this was the wrong move, okay. Here, it's total energy. Because, first of all, we need total energy to estimate this transition temperature, but in this case, crack initiation energy was very low for all areas, for all zones. So total energy is practically the same as crack propagation energy at -60. And this is why we didn't care too much about separation of energies in this case. So that's all for me in respect to presentations.